So yesterday we looked at some theoretical aspects of Laplace transform, but since many of you asked about applications, how to apply these theories, so let's talk about applications. So today I will talk about applications of the Laplace transform to solve differential equations okay. So mainly linear ordinary differential equations with constant coefficients. But then also to look at examples in physical systems. So once we know how to apply Laplace transform to solve a differential equation, then we can use it we can apply it in many examples where physical systems are modeled on differential equations. So probably you know that many physical theories have differential equations as their model. Okay. For example, if you have a spring, just the simplest example of a spring, and a mass attached to the spring, what is the differential equation which governs the displacement? So let's suppose that this is the equilibrium position. This is x equals 0, this x equals xt depending on time. So what is the differential equation that governs the displacement of the mass? Anyone? So you all know this. Yes. So d2x over dt2 equals minus some constant times x. Okay. So this is a second order differential equation with constant coefficients. So we can apply, so if we know how to apply the Laplace transform to solve differential equations, we can apply our theory to these kinds of physical systems where it is modeled on differential equations. Okay. So we will look at this kind of examples, but first we need the definition of an inverse Laplace transform What is the inverse Laplace transform? If Fs is the Laplace transform of some function ft, okay, then this input f is called the inverse Laplace of Fs. So it's just some terminology that takes you from the output towards the input, not the way we have seen. We have always gone from input to output. So we also need a way to go from output to input. Okay? And this will be used to solve differential equations. So for example, what is the inverse Laplace transform of 1 by s plus 2? example, e to the minus 2t. So in most cases, you will know, at least in the examples that we will see, you will know it will be easy to compute inverse Laplace transform. If I give you a very complicated function here, then it might be difficult, and then you have to use some complex analysis to find out first if the inverse Laplace transform exists and what is it. Okay. So another question is whether, when you're talking about inverses, when is the Laplace transform 1 to 1? Someone I think you asked, right? When is it 1 to 1? So one solution to this is called Lurch's theorem, which says that if ft and gt are continuous functions on 0 infinity, okay, and of exponential order alpha, then and moreover, and so they are continuous on the positive real line, they are of exponential order alpha, and their Laplace transforms coincide. Okay, for s greater than alpha, then ft is equal to gt. Okay, so this is a condition where the Laplace transform is a one-to-one function on the space of continuous functions of exponential time. Right? Okay. When you are solving differential equations, so now let me give you an example. So this is an initial value problem, x dot plus 5x equals e to the minus 2t, where x 0, let me take it 0. Okay, this is an initial value problem. How do you solve it? Just take the Laplace transform on both sides. Okay. Laplace transform of x prime, x dot, plus 5 Laplace transform of x is, what is it? 1 over s plus 2. And you know that this is s times, so let me call x, capital X s, as the Laplace transform of small xt. Okay, so x dot is clear. X dot is just the derivative dx by dt. I think you all know this notation. So what is the Laplace transform of the derivative of x? So s x s minus x of 0. But what is x of 0? Is I've taken it to be 0, so you don't get anything, plus 5 x of s is 1 over s plus 2. So what do you get? xs is 1 by s plus 2, s plus 5. And then you can separate using partial fractions. So what is it? 1 over s plus 2 minus 1 over s plus 5, and then you have a 1 by 3. So to find out the solution, you need to apply the inverse Laplace transform here. So what is xt? This is the inverse Laplace transform of xs, and this is, so one thing to note about the inverse Laplace transform is that it is also linear. Okay, so you can use that linearity property 1 over s plus 2 minus L inverse 1 over s plus 5, and now it's easy. So this is 1 by 3 e to the minus 2t minus 5. Okay? So here, if you look at it carefully, you will see that this part is the solution to the homogeneous problem when x dot plus 5x is 0, then you get this part, and this is a particular solution to this. Okay? So someone was asking whether you get a particular solution or a general solution. So in it you get a general solution. Okay. Let me do another example. So this example is x double dot plus ax is f of t. Plus or minus? Sorry, minus a squared. Okay, and x0 is alpha, x dot 0 is beta. Yes. So yeah, let me put a double dash. It's easier to see. So here we are assuming that the Laplace transform of ft exists. Okay, we can assume it to be of a continuous, of exponential order. Okay, all you want. Okay, so take Laplace transforms on both sides. What will you get? S squared xs minus s x prime 0, which is beta, minus sorry? Yeah, sorry. Yes, thank you. Alpha minus beta, this is f of s. So f of s is the Laplace transform of f of t. Yeah, I forgot. Thank you. Sorry about that. Minus a square of xs. So you can collect the terms for xs. xs equals fs plus s alpha plus beta. Okay, and then x of s is 1 over s square minus a square fs plus s alpha plus beta minus s squared minus a squared. So you can further separate out into two parts, alpha s plus beta 1 over s squared minus a squared. Okay? Now here one has to use something. Okay? Here this is a Laplace transform, a product of Laplace transforms of two functions, right? So I think you know already how to do this. What is the convolution theorem? It says that the Laplace transform of convolution of two functions is the product of the Laplace transforms, right? So you use, I didn't say about it earlier, but I think all of you know. So convolution theorem says that L of f star g is f s g s. Right? What is f star g? F star g t is integral over 0 to t f of u g of. Very good. So the convolution theorem says this. So here, when we take the inverse Laplace transform, we can write it. So what is the inverse Laplace transform of this guy? Hyperbolic sine. No? This is hyperbolic sine, this is hyperbolic cos. Okay. So how can we write it in convolution form? This is integral 0 to t ft hyperbolic sine of at 1 over a dt u minus t or t minus u. This is u, this is u. So this is the convolution of f and hyperbolic sine. When you take the Laplace transform, it will be a product of the Laplace transform of f, which is fs, and Laplace transform of this, which you will get this. Okay. Similarly, you get the other terms. So this is just alpha cos hyperbolic cos of at plus beta sin h at, and this 1 over a is, or I think the whole thing. Let me check. No, just so here there is no 1 over a. It's just over this one actually. Okay. So just to give you an idea how to solve differential equations. Is it clear until now? The process is clear? So this goes back to the idea about solving a differential equation through an algebraic equation. So what was the square? So you have a differential equation in x or in u, let's say x. You want a solution to this differential equation. Okay. So by Laplace transform, you convert it to an algebraic equation which is in S, the Laplace transform variable. Okay. You solve this algebraic equation. So this will be in S and XS. Solve for XS. Okay. And what is this arrow? Just the inverse Laplace transform. Okay. When will it be invertible? Yeah, so This has to do with the singularities of Fs in the complex domain. Okay. So I don't want to go into this. Okay. Maybe later we can discuss about it. Okay. So this inverse Laplace transform has an expression in terms of a complex integral, is a contour integral. Okay. So this contour integral will give you should be convergent. So it's actually it's on the total imaginary axis. So L inverse of Fs is given by 1 over 2 pi I limit of t tends to infinity integral c minus I t to c plus I t e to the t s fs ds. So this is a complex integral where you have a contour which is the entire imaginary axis translated left or right, so that the singularities of Fs are removed. Okay. So for example, if your f is an analytic function on the right half plane, then it will give you something. Okay. Sorry? Okay. So let's see what. I just want to quickly give you another formula. This is called Heaviside expansion formula. This says that if Ps, so this is one answer to your question, okay? Qs are polynomials, degree of P is less than degree of Q as polynomials, okay? And P and S and P and Q do not have a common root, any common root. So now when I'm talking about root, this could lie in the complex plane. Okay. Further, suppose that Q has n distinct roots, alpha 1, alpha 2, alpha n. Okay. Then L inverse of PS over QS exists first, and is given by the formula I equals 1 to n P of alpha I over Q prime of alpha I e to the alpha I t. Is this equation familiar? Is this formula? No? Okay. So let me prove it. So by assumption, P and Q are not very complicated, they are polynomials. Okay. Then since Qs has n distinct roots, we can write Qs as the product of s minus alpha 1, s minus alpha 2, s minus alpha n. Okay. Then Ps over Qs can be expanded using the method of partial fractions, okay, and can be written in terms of a sum a1 by s minus alpha 1 plus a2 by s minus alpha 2 plus an by s minus alpha n. Do you agree? Okay. Now let's multiply on both sides by some alpha I, okay, by some s minus alpha I. So let's take Ps s minus alpha I over Qs, okay, and take the limit as s goes to alpha I. So the left hand side is this. What will be the right hand side? So you are multiplying each term by s minus alpha I on the numerator. Sorry? Exactly, yes. Because it has distinct roots, right? All the alpha i's are distinct, so there will be no possibility of having poles, okay? And when you take s going to alpha I, everything other than ai will vanish. So this is just ai, okay? Here one can use L'Hopital rule, okay? Because when s goes to alpha I, this is going to 0 and this is also going to 0, okay? So one can use L'Hopital rule. So what will you have? As s goes to alpha I, P of s over Q dash of s plus s minus alpha I P dash of s over wait. Yes, it's okay. So when you take the limit, this part will vanish because you have an s minus alpha I term, okay? Here what you get? P of alpha I over Q dash of alpha I, okay? So the left hand side is P of alpha I over Q dash of alpha I, and on the right hand side you get ai. So we have in fact identified these coefficients in this partial fraction expansion in terms of P and Q. Right, so L inverse of Ps over Qs what will it be? This is the L inverse sum over I from 1 to n, L inverse of AI by S minus alpha I, but we already know what is AI. So this is I from 1 to n, P of alpha I over Q prime of alpha I, and L inverse of 1 over S minus alpha I. So this is I from 1 to n, P of alpha I over Q prime of alpha I, and what is this? E to the alpha I t, which is what we wanted. Okay. It's not very difficult, but useful formula whenever you have a rational function in S. Okay. Very good. Okay, so let me now go to applications in physical systems. So I'll not spend too much time in solving differential equations because I think all of you have already have experience in doing so. So let me just give some applications in the physical world. The main idea is that the physical process, many physical processes are given by differential equations, and their solution can be found by using Laplace transform techniques. This makes the Laplace transform technique a very powerful tool in physics and engineering. Okay. So let's start with applications. Physical systems. So let's start with mechanical problems. So let me go back to the spring problem. So you have a mass m connected to a spring, and its displacement is xt at t equal to time equals t. Okay. The differential equation which governs the motion of the mass is given by m x double prime equals minus kx. This is called Hooke's law in physics. Now let me try to complicate it a little bit more. Suppose that there is a dampening term which is proportional to the instantaneous velocity of m. So this is given by some constant mu times x prime. So this is mu dx by dt, and this is the dampening term d mu. Okay. When this exists, you have to take it into account in this equation. So then your equation will be mx double prime plus kx equals minus mu dx or x prime. Okay. So here mu is positive, k is also positive. Okay. what does it mean to have a dampening term? It means that the higher the velocity, okay, the more the friction will be. Okay. So because here you have mu positive, so if this is large, the dampening term will be large. Okay. So let's try to solve this kind of problem. So you have m x double prime plus mu x prime plus kx equals 0. Now let me take initial conditions x0 equals x naught and x prime 0 equals v naught. So this is an ordinary differential equation with given initial values with constant coefficients. Okay. So then Laplace transform technique is applicable. So just take Laplace transform on both sides. What will you get? L. So first, let me. So in physics they change the terms a bit. Okay, that makes the analysis easier. Mu by m x prime plus k by m x equals 0. So put alpha equals k over 2m, omega equals mu omega square is mu over m. If I'm not incorrect. No, it's the other way around actually. This is mu, this is k. And you'll see how this this makes things easier. Yeah, this is correct. So what do you have? Plus 2 alpha m, 2 alpha x prime, because there is a 2 here. So we have to multiply with the factor of 2 plus omega square x equals 0. Now you take the Laplace transform. So what do you get? So Laplace transform SXS minus s squared xs minus s. What is x naught? x0 is x naught. Yes, sorry. Minus v naught plus 2 alpha s xs minus, what is it? x0, this is x naught again, plus omega square xs. This is okay? It's okay? Okay, so now let's try to solve for xs. So you have s square plus 2 alpha s plus omega square xs equals sx naught plus v naught. Are there any other terms? Plus 2 alpha x naught. Right? So xs equals sx naught plus v naught plus 2 alpha x naught over s square plus 2 alpha s plus omega squared. Okay. What you can do is add alpha square and subtract alpha square. Okay, then what do you get? Then the denominator is s plus alpha whole square plus omega square minus alpha square. And now the behavior of the system will depend heavily on this term, right? Whether omega square is greater than alpha square, omega square equal to alpha square, or omega square is less than alpha square. Okay. Okay, so let's try to take the inverse Laplace transform in the case 1, which is omega square minus alpha square is positive. So then, what is it? L inverse of xs equals sx naught by s plus, so L inverse of alpha square plus omega square minus alpha square plus v naught plus 2 alpha x naught by this same. Okay, is this familiar? Right. So, in fact, this is translation by e to the minus alpha, and then you have a cos term, yeah? And this one is translation e to the minus alpha times sine. So this is, sorry? S plus? Yeah. You are absolutely correct. So this is alpha x naught minus alpha x naught. So in fact, you will have two terms. Yeah, okay. So thank you for this. So this is s plus alpha x naught plus omega square minus alpha square plus this one will hit this one. So v naught plus alpha x naught by s plus alpha square plus omega square minus alpha square. Right? Yes. So then you can write this in terms of cos and sine. So this is cos of omega square root of omega square minus alpha square exponential, what is it? Minus alpha t. It's okay? Second term is v naught plus alpha x naught sine square root of omega square minus alpha square exponential minus alpha t. It's okay? Yeah. Thank you. I'm making stupid mistakes today. Divided by? Yes. Making a lot of mistakes. Yes. Thank you. Right. So, what is the behavior of this system? Suppose that alpha is 0, okay, which means that the dampening coefficient is 0. Then this is 1, this is also 1. So you have a combination of cos term and sine term. Then what will be xt? What will it look like? It will just be some oscillatory function. Okay, it's just a sum of oscillatory functions. Okay, so it's something like this. Okay, but we have a dampening. If we have a dampening factor mu positive, then as t tends to infinity, you see that this goes to 0. This is bounded. This is bounded. This also goes to 0. So in fact, it will oscillate, but the oscillations will die out. Sorry, I'm very bad at making pictures. Something like this. Okay, the amplitudes will die out. So, as you can see, I'm very bad. Anyway, so this is the damped oscillation where motion will die out. So when you have a spring, this is the equilibrium position, this is xt. If there is no dampening factor, it will be like a pendulum, yeah? It will oscillate around this equilibrium position. But if you have a dampening factor, the oscillations will die down and it will come at rest at infinity. Okay? So similarly, you can analyze the cases where omega square minus alpha square is 0. Okay. So this part is 0, right? Then what are you left with? Xs is Sx naught plus V naught plus 2 alpha x naught divided by S plus alpha squared, right? So again, we would like to take S plus alpha here. So let me write S plus alpha x naught and take it away from here. Is this okay? So what is the inverse Laplace transform of this? E to the minus alpha t x naught plus V naught into t plus alpha x naught t okay. So this is xt. What is the behavior of the system in this solution? As t goes to infinity, all terms go to 0. Okay. So it decays like this. Okay. Actually, this is called a critically damped system, because if you move the dampening coefficient even a little bit, it becomes positive or negative, and then the behavior of the system can change very rapidly. From dampening of oscillations, it can go to, without oscillations, going to 0. Okay. The same thing you can do when omega square minus alpha square is greater than 0. And let me just write down the answer. Yes, sorry, less than 0. So what is this? This is in terms of hyperbolic sine and cos. This is x naught hyperbolic cos alpha square minus omega square t plus v naught plus alpha x naught by alpha square minus omega square hyperbolic sine alpha square minus omega square t. So in fact, the behavior is very similar to the one here, except that it does not go to 0 exponentially, but a bit slowly. So it's something like this. Okay. It also goes to 0, but slowly. So is it a nice application of Laplace transform? So we'll see some more applications. So this is about beams. So in civil engineering, you study about the stress and load on beams. So this is a beam, okay, and you can have some weight Wx. So Wx is the mass or load at x. Okay. So let me put x equals L. And what civil engineers like to do is to find out, when you have a weight on a beam, how does it bend? Okay, deflection of the beam. So when you have some weight, it will deform into something like this. Okay, and civil engineers would like to know what is the shape of the deflection, so that the beam does not break. You have to adjust the load so that beams do not break. That will be disastrous. Then we will not be able to stand and sit on a building, right? Okay. So physicists found out that so this is also again modeled on a differential equation. And what is the differential equation? Huh? Yes? No, it's a fourth order, d4 over dx4. So let me call this deflection y at x. So y equals wx over EI, okay, where E is the so-called Young's modulus, isn't it? Young's modulus. And what is I? What is I? Even I forgot. Moment of inertia. Yes. Moment of inertia. So let's take these as constants, okay, for our purposes. Only we'll allow W to depend on X, but E and I are constants. So now this is a fourth order equation. So usually we would require the conditions on Y double prime, Y triple prime also. Okay. So let me give one example. So suppose W X is constant. Okay. Suppose that the weight is constant. Okay. And we also let Y0 equals 0, Y prime, or is it double prime? Double prime equals 0. At L, this is also 0, and Y double prime L is also 0. Okay. Yes. So let's try to apply Laplace transform technique to this. So what do we have? We have d4 y over dx4 equals some constant k. This is a constant, this is a constant. So we have some constant k. So when you apply Laplace transform to the fourth power, what will you get? S4 ys minus s cube 0 minus s squared y dash, yes, minus s. So maybe we are missing. Yeah. So this is y double prime actually. Sorry, I made a mistake. Yeah. I made a mistake. So this is y prime. This is s times double prime 0 minus triple prime 0. This is k over s. So we are taking the Laplace transform, so there will be a s. So what are all 0? This is also 0, yeah? So this is 0. So you get S4 ys minus s squared y prime 0 minus y triple prime 0 equals k by s. Okay. So let me call this C1 and let me call this C2. And we have to find out C1 and C2 from the next two conditions, boundary conditions. So ys, let me write it straight away. This is 1 over s to the power 4. You have k by s plus C1 s squared plus C2. Okay, So now the inverse Laplace transform is not very difficult to compute. Yeah? So this is k over s to the power 5 plus c1 by s squared plus c2 by s to the power 4. Just compute the inverse Laplace. What will it be? T to the power 4 by 4 factorial k times plus c1 t by 2 factorial plus c2 t cube. Yes. So just t, and this is 3 factorial, yeah? T cube, sorry. Okay. So now you have two constants unknown, C1 and C2, but you have two other boundary conditions to solve them. So this is yt. So y at L is 0. Okay. So this implies k L to the power 4 by 4 factorial plus C1L plus C2 L cube by 3 factorial is 0. Similarly, you have to differentiate twice this formula, and so let's differentiate twice. Okay, so y prime t is k t cube by 3 factorial plus c1 plus 3 c2 t square by 2 factorial. Okay, y double prime t, what is this? So c1 goes away. You have kt square by 2 plus c2 t. Okay, now you know that y double prime at L is 0. Okay, so then c2 is minus kl by 2. Okay, it's clear? And so you can just plug in here the value of C2 and you can find C1. So let me just write down the answer. C1 is k L to the power 5 by 24. Just compute that this is true. So in fact you have the solution k to the power 4 by 4 factorial plus you know C1 t plus you also know C2 t cube by 3 factorial. Okay, is this clear? So let me do another example. This is called a cantilever beam. I don't know why, because I don't know much about these things, but I can relate it with mathematics. Yes. As far as it is modeled on differential equations, I can try mathematical tools. Right. So suppose an engineer comes and he says to you to help him to solve some physical problem. What will you ask him? Give me the differential equation, right? Or you work with him to model this problem on a differential equation or some other mathematical model. And this is a vast area of mathematics called mathematical modeling. Okay. Many things can be modeled in many different ways, in using statistics or probability, using differential equations and so on. For example, the spreading of infectious diseases, do you know? They can be modeled using differential equations. Okay. Now, in engineering, I was also reading about some computer control system. In control system theory, there is something called a PID controller, proportional integral differential controller, which is in mathematical terms, it is an integral differential equations, which means it's a differential equations, but it also has integrals in it. So what is an integral differential equation? So it is something like dy by dt equals integral 0 to t y u du plus some function t, okay, with given some initial values. Okay, so this has a differential and an integral. Okay, and you have to find the solution for y, and this is again susceptible to techniques of Laplace transform, because you know what is the Laplace transform of a derivative, you know what is the Laplace transform of an integral. Okay, and then you can try again to transform this into an algebraic equation in the same way, except sometimes you will not always get algebraic equations depending on coefficients. You might get another differential equation to solve, but sometimes it happens that the differential equation that you get after you apply Laplace transform is easier to solve. Okay. So I will talk about this tomorrow. So as you can see, there are many applications of Laplace transform in physical systems, in engineering, because they are modeled on differential equations. Okay. So I was talking about this cantilever beam. So this is also a beam, okay, but it's fixed again on this kind of thing, and it has some load, okay, like this, Wx, except that this end is free. Okay, this end is now free. So again, the differential equation is still the same, okay, but in the boundary values are different. So let me just give an example. So suppose the Wx is a constant weight W naught for 0 less than x less than or equal to L by 2 and 0 elsewhere, which means that you're putting load only on the initial half, the first half of the beam, and the rest of it is free. Okay. So how do you model this? This is again, I should write the boundary conditions. So y0 equals y prime 0 equals 0, y double prime 0, at L is 0, and y triple prime of L is 0. Okay, when I was reading about this, I did not understand what is the physical interpretation of the double derivative and the triple derivative. They claim that it's describing some forces, some shear forces. The triple derivative is given by the shear force, and the double derivative, I think it's called bending moment. Okay, but I cannot explain, unfortunately, what these mean. But mathematically this makes sense. Okay, this is a differential equation with given boundary values. Okay, and you have assigned Wx to be a nice function. So how do you write Wx, which is something constant on the first half and then 0? Any ideas? So we use the special functions that we studied, and here we will use the yes, exactly. So we use the Heaviside step function. So we can write Wx equals W naught u of x minus u of x minus L by 2. Okay, let's check that this gives you the right answer. What is u of x for x less than 0 is 0. Okay, so this is u of just x minus 0. So let me draw a picture. So u of x is 0 for x less than 0, and it's 1 for the right half. What is u of x minus L by 2 for x less than 0? It's 0, and it is 0 until L by 2. Okay, so this is u of x minus L by 2, and this is u of x. Is it okay? So, yeah, between 0 and L by 2, what is it? This is 1 and this is 0, right? This part is 0 between 0 and L by 2. So what do you get? Between 0 less than x less than L by 2, only this one is 1 and this is 0. So you get W naught. Okay? What is it after L by 2 less than equal to x less than equal to L? This part is still 1. It's still 1, and this is also 1, right? So 1 and 1 cancel out, and you get 0. And this is this function. Okay? So this is a way to model things that abruptly end. So unit step functions are used to model signals. For example, it is like switching on something. Okay, so when the signal is switched off or switched on, this is modeled by the unit step function. Okay, because unit step function is 0 and then 1. Okay, when you switch on some light, it was 0 before and then it became 1 suddenly. Right, it's the unit step function. Similarly, if I say that Wx at one point x equals a is some very high value W1 just at a single point. Okay? So, yeah. How do you model it? Dirac delta function. So this is the physical application of Dirac delta function. It's like a blow, okay? Impulse. That's why it's called an impulse, because it's a high amplitude force applied for a very short time, right? And here it is a high load applied for a very short distance. Okay, so that's why this can be modeled on a Dirac delta function. So this is in fact Wx equals W1 delta of x minus a. Okay, and you know that Heaviside step function, Dirac delta functions, and we know their Laplace transforms, so we can use it in our differential equation to solve it. Okay, right, so we have d4y by dx4 equals, what is it, W naught ux minus u of x minus L by 2. Right? Okay, so then we can apply Laplace transform on both sides. You know already what this will be, right? You know the Laplace transform of Heaviside step functions, and this is a linear function, so you can just take the difference of the two. Here you will have a similar thing like before, and you can do exactly the same process to get your answer. Is it clear? Yes or no? Yes? Okay, very good. Same for this one. If you have W1 delta of x minus a, can you solve this? Exactly the same process. Okay? Very good. So I think time is up for today. Tomorrow I will say something about integral equations and integral differential equations. Okay, how to apply the Laplace transform to solve this.